Our speaker today is Naomi, and her title, as you can see there, is the Farrell-Jones conjecture and automorphisms of relatively hyperbolic groups. Please, Naomi, go ahead.
Thank you very much. Thank you very much for the invitation. I'm going to talk about a paper which hopefully is nearly finished going through the journal process. We have been sending off proofs this last week with Yassine, Guerch, and Hughes, where we proved that the Farrell-Jones conjecture is true for some automorphism groups of relatively hyperbolic groups and for some semi-direct products of relatively hyperbolic groups by Z. I'm not at all sure what the background of this audience is. And also I had a very, very busy May. So there might be a couple of weirdnesses in the slides anyway, and you should feel free to interrupt me. But also if I'm just assuming that everyone knows what a finitely presented group is, and in fact I should slow down and talk about that, you should also interrupt me. Okay. I'm only on my laptop, so you might need to say something to get my attention. But okay, that being said, let's get going. The first thing, since it's a slide talk, I can do the fun thing of putting pictures on the slides. The Farrell-Jones conjecture is slightly unusually, in my opinion, among conjectures named after two people. It's named after the right two people, and they meant to say the conjecture as we now give it. You can find the paper. It's called Isomorphism Conjectures in Algebraic K-Theory. It really exists in this form. And what they were actually interested in was, I think, the Borel conjecture, which is about classifying manifolds. And they sort of realized that they kept on doing the same thing. And they thought, hey, maybe we'll write down this conjecture that we're using every time. So what does this conjecture say? It's a very abstract conjecture. It says this in its simplest form. The projection from E double under bar G, whoever that is, to a point, induces an isomorphism between some equivariant homology theory, HNG, of this E double under bar G, whoever that is, with coefficients somewhere a little alarming, to Kn of Rg. And now I've not told you what any of these objects are, so that's a bit unfair. So I'll do that now. So G is supposed to be a group. You should think of an infinite discrete group. Yeah, probably finitely generated or finitely presented. E double under bar G is what's called its virtually cyclic classifying space. So this is very hard to imagine. I find it very hard to imagine. So the definition is it's a space, it's a CW complex, which is contractible and has an action of your favorite group G. And the action has the property that for a finite or virtually cyclic, so a copy of the integers subgroup of G, it acts with fixed points, and the fixed point sets themselves are contractible. But if you picked a subgroup which was bigger than that, so a free group or a free abelian group of rank 2 or something, then it acts without fixed points. If you know about the Cayley graph of a free group, you can imagine that and then coning off all of the axes of all of the elements. And then you can think of just this one point space as a space with a G action. The action is trivial. And so this projection is secretly this right-hand side is some homology theory involving the trivial action on a point. This is an equivariant homology theory, which means I'm taking account of the fact that I'm taking homology of a space with a G action. If you were working with a free action on a space, so if you think about the fundamental group of a topological space and its universal cover, then taking the equivariant homology of the universal cover with respect to the action of the fundamental group would recover the homology of the original topological space you thought of. Because this action isn't free, infinite cyclic subgroups need to fix points, it's going to do something slightly different to that. We're taking coefficients somewhere, as I said, perhaps a little alarming, certainly a little alarming to many group theorists. In the K-theory spectrum for your favorite ring R, this is spectrum are not going to come up after this slide. So if you don't like it, they're going to go away. This is the one sentence justification I have is that the homotopy theorists really have worked out the best way to do homology in its most general form. And so this is the object which has to go here. And then what we're finding on the right-hand side of this alleged isomorphism are the algebraic K groups for the group ring. So the group ring is finite formal sums so the sums are indexed by the elements of the group, and then for for finitely many of those group elements, you get a ring element. Addition works in the obvious way, and then to multiply, you allow the group multiplication to have an effect. So the group ring will be, for instance, the group ring is commutative if and only if the group you first thought of is abelian. Okay, so this is still quite an abstract thing. The algebraic K groups are themselves quite abstract. K0 is relatively concrete. K0 is what you get if you take all of the projective modules over your favorite ring. My favorite ring today is RG with direct sum. This forms a monoid, but it's very much not a cancellative monoid. So you can take this Groton deconstruction and that spits out a group. K1 is the abelianization of the direct limit of all of the general linear groups over your favorite ring. And then there's a Kn for every integer, positive, negative as well as positive. And so this is somehow quite a lot of data. It's also not 100% obvious even which side of this isomorphism is supposed to be the thing you're interested in. The answer is the right-hand side. It's the sort of algebraic information about the group ring is what you're hoping to get out. And you're hoping to get it out because although the homology theory on the left-hand side looks quite wild, somehow the philosophy is that because the fixed points, the subgroups with fixed points are relatively easy to understand, we're sort of hoping to push the problem into understanding the integers and subgroups a bit like the integers. There's also a version for L theory. So these L groups on the right are not quite the L groups that come up in surgery theory. They're closely related to the L groups that come up in surgery theory. You get different decorations instead of minus infinity if you're doing that. In nice situations, they do agree with the ones you get from surgery theory. And they have a spectrum as well. That's what's hanging out on the left there. Okay, right. So, yeah. That's what. Here are some abstract things which are supposed to be isomorphic. But then why would you want to know about this isomorphism is an excellent question. And so I mentioned to begin with that Farrell and Jones were interested in the Borel conjecture, and I will cycle back round to that. But in fact, it has surprisingly many applications, sort of to surprisingly disparate things, at least to me. So one thing, of course, is that you might want to understand the objects in the conjecture. So if you care about group rings, you might care about things like the Novikov conjecture. This is about the L groups over ZG, I think. And you might care about the Bass conjectures, about the structure of the group ring, or even just the K theory of the group ring. If you care about group rings, you've heard about group rings, you might have heard about the Kapansky conjectures. There's 3 or 4, depending on how you count. There's one about what the units should look like. There's one about what the zeros should look like. This one is about what the idempotence of a group ring should look like. So it says that if you put in a torsion-free group, then, and I didn't put any hypotheses on the ring, I probably should have done. Definitely the integers, anything reasonable. The only idempotence of the group ring is 0 and 1. And in fact, this conjecture follows from the vanishing of, this is the reduced K0 of the group ring, and the vanishing of the reduced K0 of a group ring for a torsion-free group follows from the Farrell-Jones conjecture holding true for that torsion-free group. So those are consequences about the objects in the conjecture. There are also some consequences a little bit further away. So for a torsion-free group, we can get control, which means vanishing, identically 0. of the Whitehead group of G. So this is some co-kernel of the first K group of ZG. And if there's an object called the Whitehead torsion who lives inside the Whitehead group, and the Whitehead torsion is if you have a homotopy equivalence between two spaces, the Whitehead torsion is an invariant of that homotopy equivalence. And if it's 0, then you can upgrade your homotopy equivalence to a simple homotopy equivalence, which is about you have a CW complex, then you're just adding and removing cells in a very constrained manner. And what can you generate by doing this? And so this is kind of, you can maybe see how this is heading back towards manifolds. So you start with a map which does not have very many nice properties, and upgraded, I mean, is homotopy equivalent to. And so you want to gradually, step by step, you want to take your map without many good properties and upgrade it to have nicer and nicer ones. There's also Wall's finiteness obstruction, who lives again in this reduced K0 of ZG. So this says that finitely dominated CW complexes, which I don't really, it's not a definition I really want to give because it's not coming back. But it says that they're homotopy equivalent to finite CW complexes. And again, this is a way of saying, if I have a space which is quite nice, but not as nice as I might have liked it to be, and this finiteness obstruction measures if, in fact, that I could have just written down a finite CW complex to begin with. A downstream consequence of this, which comes up in my research slightly more often than I want it to, given that we haven't yet proved that the relevant groups satisfy the Farrell-Jones conjecture, is that it's currently open if a group is torsion-free and has a subgroup which is type F, so it has a finite classifying space. It acts co-compactly on a finite dimensional CW complex. We don't know if the group you first thought of is. We don't know if you can upgrade that from the finite index subgroup yet, which is a little bit annoying. This consequence goes via the Eilenberg-Guerch conjecture. That's sweeping many things under the rug where I wish for them to stay.
Sorry, could you repeat what this problem of distinguishing VF from F is? V is, I suppose, is virtual, right?
V is virtually, yes, exactly. So VF says you have a finite index subgroup, which is type F. So should act co-compactly on a finite dimensional CW complex. And if you have torsion, you can't be type F on the nose because having torsion freely co-compactly, I missed a word. There we go.
Okay.
Right. So finite groups can't act freely on any finite dimensional CW complex. So being torsion free is necessary. But surprisingly, you have to be very careful sticking together finite index subgroups. You can do this product construction and get an action on a finite dimensional CW complex, but unless I have forgotten something, which I don't think I have, that's generally not co-compact, although it's free. Okay. Any more questions while I'm paused? Okay. Thank you for that. Right. Onwards. So this is the Borel conjecture, I believe, is the original motivation in sufficiently high dimensions. So the Borel conjecture asks, if I have two closed orientable aspherical D-manifolds, aspherical means that the higher homotopy groups vanish, so there's no the pi 2 or pi 3 or so on. There's just a pi 1 and then everything vanishes. And I have been given the information that the fundamental groups of these manifolds are isomorphic. Is it true that the manifolds you were thinking of homeomorphic is what I mean by the symbol here. the question is false if I was asking for diffeomorphisms. And the answer is no if I was asking for diffeomorphisms. And okay, so in low dimensions, this question is not so hard. In dimension 2, this follows from the classification of surfaces. So more or less any invariant you can write down of a closed surface is going to allow you to say that if the fundamental groups were the same, then the surfaces were the same. Even in dimension 2, you can see that closed was a necessary condition. If you take a surface and add many punctures, then you can change 2 punctures for one more genus without changing the fundamental group. In dimension 3, the Borel conjecture is true, and it follows, as so many facts about 3 manifolds do, from the resolution of the geometrization conjecture. It follows in the sense that it was known for many years before the resolution of the geometrization conjecture that it would imply the Borel conjecture. But you have to do all of this decomposition theory for 3 manifolds to check. You also, lens spaces are going to run you into problems if you forgot to say aspherical, even in dimension 3. And then in dimension 5, it holds, for instance, by Farrell and Jones, it holds for non-positively curved, compact, connected Riemannian manifolds, and for manifolds whose fundamental group is hyperbolic or cat 0. Did I? No, I didn't. And these proofs come from proving the Farrell-Jones conjecture for your group. And again, to sort of say things very quickly, this uses quite a lot of the things in the previous slides. So you get vanishing of the Whitehead group, because the fundamental groups have to be torsion-free, otherwise the manifolds can't have been aspherical, for the same reason about finite groups not acting on freely co-compactly on finite dimensional spaces. That lets you pass the homotopy equivalence that you actually had from here because they were aspherical spaces. You can pass from this homotopy equivalence to a simple homotopy equivalence. You also get this vanishing of the reduced K0 and the negative K groups, which lets you say that the L theory version of the Farrell-Jones conjecture was equivalent to talking about the L groups that come up in surgery theory. And then you can use the L theory version of the Farrell-Jones conjecture and the Atiyah-Herzebruch spectral sequence and the Rothenberg sequences and many non-trivial things to conclude that you can upgrade your simple homotopy equivalence to a homeomorphism, and the Borel conjecture is true. So it's a very abstract algebraic statement, and then it has some surprisingly concrete, highly non-trivial topological consequences. And the last thing I want to say is that maybe you've written down a manifold that wasn't aspherical. And you can also, if you want to try and classify these, then the Farrell-Jones conjecture helps a bit here as well. So for instance, Crack and Luke have some rigidity results, Borel conjecture type results for some bundles, like bundles of 3 spheres over surfaces. And then there's a couple of papers from 5 or 6 years ago, I guess now, classifying things like torus bundles over lens spaces. And so these spaces aren't aspherical, so the Borel conjecture is not exactly the right question to ask. But again, sort of understanding the fundamental groups of these spaces and the properties of the group rings that the Farrell-Jones conjecture gives you is an ingredient in these results, understanding these manifolds. Okay, that's the end of me trying to tell you why you should care about the Farrell-Jones conjecture. I'm now going to tell you a bit about some groups which I know which satisfy it. Okay, so the Farrell-Jones conjecture is satisfied by many groups. Currently, there are no groups that we know that don't satisfy it. So this list is incomplete, almost certainly. Also just for what's in the literature today. So the list includes hyperbolic groups. These are groups with a negative curvature condition on their Cayley graph. On the other end of kind of the negative curvature to positive curvature spectrum, solvable groups also satisfy the Farrell-Jones conjecture. Arithmetic groups, and in fact S-arithmetic groups, so you're allowed to invert finitely many primes. The mapping class group of an orientable surface. And getting towards the things I want to talk about today, semi-direct products where G is free and the quotient group is cyclic. And then, in fact, shortly after they put the first version of this paper online, they realized that they could upgrade to G being hyperbolic and virtually torsion-free. So the free groups paper never got published because it got subsumed into this hyperbolic and virtually torsion-free paper. And then many more as well. This is not an exhaustive list. It's an exhaustive list of everything I'm going to need later on in my talk. And then to say the groups that I was working on with Sam and Yassine, we were thinking about hyperbolic groups. So G is the group, P is a family of conjugacy classes of subgroups of G. And if G is either virtually torsion-free or one-ended, I'll say what one-ended means a bit later, and P consists of finitely many soluble groups, for instance, then the semi-direct products G with Z satisfy the Farrell-Jones conjecture. And the other theorem that we have to be more restricted on G and what it's hyperbolic relative to. So if G is one-ended, a one-ended hyperbolic group, that should say, and P consists of finitely many virtually polycyclic groups. So you could think toral relatively hyperbolic and let the virtually polycyclic groups just be free abelian if you wanted. Then the automorphism group and the outer automorphism group of G satisfy the Farrell-Jones conjecture. Okay, and so for the rest of the talk, I'm going to ignore the applications of the Farrell-Jones conjecture, and I'm just going to talk about how we proved these theorems, which is somehow the conjecture is sort of in the process of moving from topology algebra towards geometric group theory. So what we did was we used geometric group theory tools to be able to sort of increase the class of groups which are known to satisfy the Farrell-Jones conjecture. Yeah, and I'm going to talk a bit about how we did that. So the class of groups satisfying, now I'm working with a stronger version of the conjecture than I stated at the beginning, which is the full fibered Farrell-Jones conjecture with coefficients in additive categories admitting finite Reith products. I think this version is the version that you have to use to get all of these inheritance properties I want to use. And it's also has no counterexamples yet. If you know a little bit about the Baum-Kohn conjecture, then the Baum-Kohn conjecture with coefficients does have counterexamples. So you can't use all of the nice inheritance properties all of the time. But for the Farrell-Jones conjecture, the version with coefficients also has no counterexamples yet. So for the time being, I'm perfectly free to use all of these nice inheritance properties. So the class of groups satisfying the stronger version of the Farrell-Jones conjecture is closed under taking subgroups. It's closed under taking finite index over groups. It's closed passing to finite direct products or finite free products. And it's closed by taking directed co-limits or direct limits, depending on how much you're into category theory and how much you're into group theory. We still call them direct limits usually. And then I'm never sure whether to put relatively hyperbolic groups as an inheritance property or as a class of groups which satisfies the conjecture. So what I mean by putting it in this list of inheritance properties is that if G is hyperbolic relative to a family of groups, and each of those groups satisfies the Farrell-Jones conjecture, so for instance, if I'm hyperbolic relative to solvable groups, then G itself satisfies the Farrell-Jones conjecture. So this is somehow an inheritance property because I put in some groups that satisfied the conjecture and I got out another one. But also it's a theorem in its own right that Bartels proved. And it's closed under taking some group extensions. Unfortunately, not all. Life would be much easier if everything was closed under taking extensions. The tagline that I like to use for it being for which group extensions work is suspensions imply extensions. So if I have a group extension, which I would like to think of as a short exact sequence, so K is the kernel and Q is the quotient. And of course, what I'd like to be true is that if K and Q satisfy the Farrell-Jones conjecture, then so does G. Happy days. This is not quite true, or at least it's not yet proved. So I am going to assume that K satisfies the Farrell-Jones conjecture. It's a subgroup of G, it had better. And I'm going to assume that Q satisfies the Farrell-Jones conjecture. Otherwise, there wasn't a lot of point using it at all. And then I also need to check that I take an infinite cyclic subgroup of Q, and I look at the full preimage in G of that infinite cyclic subgroup, and I need to check that that satisfies the Farrell-Jones conjecture. And I need to do it for every infinite cyclic subgroup of Q. But these preimages are exactly going to be semi-direct products K with Z, where the automorphism, which I need really to put here to define the semi-direct product, is going to depend on which infinite cyclic group I took.
Sorry, may I ask?
Yep.
Something? So the first statement, that the first sentence right after the exact sequence.
Yep.
Is that a theorem?
It's sort of a folklore lemma.
But it's true. I mean, it's not because you said I wish it were true, but under
Yes.
I suppose.
Well, I wish it would. Yeah, I wish it were true that if KQ satisfy the Farrell-Jones conjecture, then so does G. That is what I wish were true.
But what you know is if with this additional condition, because it that okay, yeah, okay, so yeah. That's thanks.
So I need this additional condition on all of the preimages of all of the cyclic subgroups, which is somehow yeah.
So in particular, if Q is virtually cyclic, then you don't know, and G and K satisfies Farrell-Jones, then you don't know that G does.
Not on the nose, no.
Okay.
But so this is partly why it's an interesting theorem to say that something bicyclic group, or if I can say that all relatively hyperbolic with some conditions bicyclic groups satisfy Farrell-Jones, then I'm going to satisfy this this annoying extra clause in the sentence because the preimages are all going to be hyperbolic relative to soluble bicyclic. And if my theorem says that these all satisfy the Farrell-Jones conjecture, then I know that whenever I put a hyperbolic relative to soluble group in as K and something in as Q that satisfied the Farrell-Jones conjecture, then I get that any G is okay. But I have to do this hard work to check the semi-direct products with Z first.
Sorry, very ignorant. A comment that will show how ignorant I am. So are you saying that every virtually cyclic group, I mean, so say Q is virtually cyclic and G is Q itself.
Okay.
So then the preimage is the virtually cyclic group. So it should be Z according to what you say, because K is trivial.
Yep. So these are, if you like, these are solvable groups. That would be one way to see it. The more philosophical way to see it is that if the statement of the conjecture I gave at the beginning involved this space, which the group was supposed to act on such that all of the infinite cyclic, virtually cyclic subgroups fixed something, And if the group itself was virtually cyclic, that means that this is going to be homotopy equivalent to a point.
Yeah.
And so the assembly map that was giving me the thing, which is I'm hoping is an isomorphism, is just going to be a point to a point. So the thing is going to be an isomorphism.
Yeah. No.
It has to be.
Yeah, but what I'm asking is, in this statement, right? Say K is trivial. Trivial is trivial, yeah. And so G equals Q.
Yep.
And then Q is virtually cyclic.
Yes.
So according to what you say, Q is Z. So any virtually cyclic group is Z, which is not true.
So I'm secretly using the fact that the Farrell-Jones conjecture behaves well when I pass a finite index over groups.
No. I'm saying the premises are exactly K, are exactly cross products of Z with K, right? Now, if K is trivial, as it would be, right? Then that means that Q is Z. But there are five virtually cyclic groups which are not Z.
Yes.
And so what's wrong there? Maybe you are
nothing is wrong there, but I'm allowing myself to use this fact. So if you're happy, so it's so I'm claiming, not particularly rigorously, that adding virtually here is the same as forgetting to add virtually, but remembering that I'm allowed to pass the finite index over groups.
It says every infinite cyclist for a group and not every virtual. Okay. Yeah. Now I understood. Sorry.
It's okay.
Thanks for your patience.
Any more questions? Let's not take any more confusions further than necessary. Okay, I'll continue then. How? So here is a lemma. I wasn't quite sure where in the talk to put this lemma, because the reason why you should care comes up later on. But I quite like it because it kind of uses all of the inheritance, almost all of the inheritance properties I listed. So this is quite general. G is a group. Phi is some automorphism of the group. And I want to think about the periodic elements relative to phi. So I'm going to take this set. Turns out to be a subgroup. This requires a little bit of work to show. The elements of my subgroup are exactly the elements of G, which are sent to themselves by some non-trivial power of phi. And K can vary depending on G, K might be different. And the lemma is that if G satisfies the Farrell-Jones conjecture, then so does the periodic subgroup semi-direct Z with the same phi. To check that there's an action at all, then sort of you have to check that phi commutes with phi to the K. Is the key thing you have to check to believe that this is going to be a subgroup of something. The proof is a series of bullet points. The first one is decomposing the periodic subgroup as the union of the fixed subgroups as K ranges over the non-zero integers. If at any point I put 0 in this line, then ignore it, I didn't mean to. And then because I'm happier when I get directed things, so I really want there to be inclusions one to the next, I'm going to only take the integers which are factorials. So now the fixed subgroup of phi is contained in the fixed subgroup of phi squared, is contained in the fixed subgroup of phi to the 6, and so on and so on and so on. This is still eventually going to hit a multiple of every K. And so this is going to be, this union is now directed and it's going to be the periodic subgroup. And then I can do a little bit of algebraic manipulation. And I can put the semi-direct product with Z inside the union. And then I can use, well, I wish to use the claim that directed colimits of groups which satisfy the Farrell-Jones conjecture satisfy the Farrell-Jones conjecture. So now I want to look at this group inside the brackets. And then rather than looking at phi, I can take the finite index subgroup, where I just take the kth power of the generator here. This is going to be a direct product. And then I get to use the fact that Z is a solvable group, if you like, satisfies the Farrell-Jones conjecture. The fixed subgroup is a subgroup of the first group I thought of, which I assume satisfies the Farrell-Jones conjecture. Direct products are okay, so this is okay. And then I can put these back into this union and use the direct limits thing. So this is somehow, it's not a very difficult lemma, but it's a lemma which uses a lot of the properties all at the same time in a row, which I find quite fun. And the other thing, or not the other thing, a main idea in our proof is group actions on trees. And I just wanted to sort of I haven't got time to really explain how I think about group actions on trees, but I wanted to give a little bit of a sense of what I want to do. So the canonical examples of a group acting on a tree would be the Cayley graph of a free group, which is what this is a piece of. So the vertices are the elements of the free group, and there is, in this case, a horizontal edge if you multiply by A to get there on the right, and a vertical edge if you multiply by B going up, B inverse going down. And because it's a free group and I picked a free generating set, there's no relators, which is equivalent to there being no cycles in the Cayley graph. Groups always act freely on their Cayley graphs because the vertex set is in a bijection with the group elements, essentially. And so this gives an action of the free group on the tree. You can also think of this as the universal cover of the rose with two petals, as a more topological interpretation. You can also think of a free product of, say, A star B acting on its Basset tree. And I've left up the Cayley graph of F2 because if you carefully chose A and B to be finite groups with 4 elements, then you would get the same tree, but a different action. So you have to ignore the vertex labels. You think of the 4 elements of A as fixing this vertex and, say, cyclically permuting the edges. The 4 elements of B maybe fixing this one and cyclically permuting the edges. And then if you have some product of elements of A and B, they're going to do some product of those things. And so this is not a free action because I said that A and B stabilize vertices. But carefully defining it, you check that the edge stabilizers are trivial. A third kind of example, I haven't drawn the tree because it's infinite valence, but you can think of the splitting of a surface group dual to a simple closed curve. Here's a surface group, here's a simple closed curve. If I cut the surface, I'm a geometric group theorist. I think of topological spaces and their fundamental groups as the same thing. This is a surface, not a surface group. But if you cut the surface along this curve alpha, you get 2 pieces. The fundamental groups will now be free. And Van Kampen's theorem tells you that this is an amalgamated product of the 2 free groups according to this common infinite cyclic subgroup corresponding to the curve alpha. And so Basset theory, like as for a free product, will give you a tree that way. If you're more topologically minded, you might prefer to find that tree by lifting the picture to the universal cover. So the curves alpha become geodesics in the hyperbolic plane. And then if you put a vertex for every complementary region and connect to and join 2 vertices if they cross just one lift of alpha, then this recovers the same tree. And now this one, sort of obviously from the definition I gave, maybe, it's an amalgamated product over this infinite cyclic group corresponding to alpha. And so this time the edge stabilizers are going to be infinite cyclic groups. And to fix some definitions for, well, I used one-ended earlier without defining it. A group is infinitely ended if it has an action on a tree with no fixed point and where some edge stabilizer is finite. Irreducible here is ruling out the cases of virtually cyclic groups, since we've already had a discussion about virtually cyclic groups. And G is one-ended if it's not finite, virtually infinite cyclic, or infinitely ended. I'm cheating a bit because this is really a theorem. The definition is about the geometry of the Cayley graph, but this is the property I'm going to use, so I'm treating it as a definition. Okay, and the useful fact for us, is that if I have a group acting acylindrically by isometries on a tree, and every vertex stabilizer satisfies the Farrell-Jones conjecture, then so does the group. The group has changed names, that's fun. An action on a tree is acylindrical if arcs longer than some k have bounded stabilizers. So I'll go back to my picture of a tree. So maybe I would allow arcs up to length 5, wherever they were, to have an infinite cyclic stabilizer, say. But then as soon as I get to length 6, then the stabilizers have to be not only finite but bounded. So there's some universal constant that says the stabilizer of every arc of length 6 is has cardinality less than 100, say. If you're being careful, you put both of those constants in the definition. In the case of these hyperbolic groups, these hyperbolic bicyclic groups, it's not so hard to produce an action on a tree. It's quite a lot more work to get an acylindrical action. And it really is necessary for Knopf's theorem that the action was acylindrical. And so how do we go about building these actions? I'm not going to spend very long on this slide, I think. So this is a very coarse picture of how I like to think about actions on trees. So on the one hand, over here, there are free actions of a free group on a tree. And I want to think about automorphisms as well. I can pre-compose my favorite action with an automorphism to get a new action and ask if I get up to an appropriate equivalence the same tree. In the case of these free actions of a free group, almost always you don't. The same tree stabilizers are finite. But over here on the other end, there's a version of JSJ theory for groups where you really do get one canonical tree, which is fixed by all of the automorphisms. And what I'm going to use today is something that we called periodic JSJs. So they play nicely with the favorite automorphism I put in, but in general, they're not at all invariant. Okay, so we have canonical JSJ trees. Eventually, thanks to Girardel-Levitt, the story begins with Jacob Schelin and Johansson and their work in three manifolds. And Rips and Seller brought it to group theory, and then many, many, many people, hopefully none of whom are here to hear me not say their names, generalized and generalized and generalized. And the version of the theory we usually use today was written down by Girardel and Levitt. We have canonical JSJ trees. The G action is acylindrical. The vertex stabilizers, I've missed some hypotheses. The G action here, G should be a one-ended relatively hyperbolic group. Otherwise, this is not true. The vertex stabilizers are to do with the original relatively hyperbolic structure. They're virtually cyclic. They're what's called rigid, or they're really trying very hard to be surface groups. They're hyperbolic two orbifolds with boundary, and there's conditions on how the incident edge stabilizers behave. The action of G, relatively hyperbolic, extends to an action of every G semi-direct Z. This is sort of the content of the word canonical. But while G acts acylindrically on this tree, the G semi-direct Z action almost always isn't acylindrical, and it's usually quite comically not acylindrical. There's an entire free group acting freely, the minimal invariant tree of that free group is fixed by something large and annoying. And the solution for us is we just force more things to be elliptic. JSJ theory is quite flexible. You can put in more subgroups that you're going to demand are elliptic. So this set, I'm allowing myself to range over an entire outer automorphism class, because this is what makes the theory go. And I'm putting in all of the periodic subgroups I defined earlier for all of the representatives of all of the powers of my favorite outer automorphism. And then this tree admits an acylindrical action of the semi-direct product I was thinking of. And then after a bit more work, the stabilizers in the action satisfy the Farrell-Jones conjecture. So for instance, some of them are these periodic bicyclic groups from the lemma I mentioned earlier. And so this is great. For the one-ended relatively hyperbolic case, we can use Knopf's theorem. We've built an acylindrical action. We've checked the stabilizers. We satisfy the Farrell-Jones conjecture. The other regime is this infinitely ended regime. And this is where we needed the virtually torsion-free assumption. So now I'm going to pass to my finite index subgroup. I'm going to assume I'm torsion-free. And so this means this is an accessibility theorem. Not only did I have an action where there was some edge with finite, hence trivial because I said torsion-free stabilizer. In fact, I can keep splitting. And so I can eventually decompose as a free product where some of the groups are one-ended, and they're still relatively hyperbolic. And then there's a free factor on the end. And the case here is an induction on this k plus this n, which is sometimes called Guerch rank because this is sometimes called a Guerch decomposition. The base case is either the infinite cyclic group or the one-ended case I just sketched. And then there are two induction steps. Either you can sort of group the free factors together and you get what's called a sporadic free factor system. So there's just A1 star A2 or A star Z. This does not in and of itself have an acylindrical action, but there's one which is not so far away. And the vertex groups, either these periodic things have come back again, or they're to do with the free factors in the sporadic system. If this doesn't happen, then you use a result of Guerch and Borel to say that the outer automorphism was relatively fully irreducible. And in this case, we're very happy because this means that the suspension G by Z was relatively hyperbolic by Darmani and Lee. And they tell you what you're hyperbolic relative to. And we're very happy because they occurred somewhere earlier in the induction. So they were one or infinitely ended relatively hyperbolic by Z groups, but there was a smaller Guerch rank. So they're dealt with by this stage in the induction. And so here we win because we're hyperbolic relative to things which satisfy the Farrell-Jones conjecture. In A case, we win because we've built an acylindrical action and we understand the vertex groups well enough. And the last theorem, so I mentioned one theorem about semi-direct products, and the other theorem was about automorphisms and outer automorphisms. And unusually, outer automorphisms come first. This is really a JSJ theorem again. This is another Guerch-Levitt theorem. So we use a short exact sequence where the middle term, which is surprisingly far to the left, is a finite index subgroup of the outer automorphism group of G one-ended hyperbolic relative to P virtually polycyclic. And it has a kernel called T and some large product, which I will now start labeling. The kernel is all of these tildes which are about to appear mean up to the inheritance properties I put on a slide earlier on. So up to some messing around with finite index and such things. This is a free abelian group times a product of the PI, which are virtually polycyclic, which is soluble, so I'm happy. Soluble? Yes, I think that's what, yeah. And then these mapping class groups are mapping class groups of orbifolds. So up to a proposition which we proved, mapping class groups of orbifolds satisfy the Farrell-Jones conjecture because of the orientable mapping class groups of orientable surfaces by Bartels and Vespina. And this last term, which is the outer automorphism group of some of these virtually polycyclic PJs relative to something. This is a subgroup. So you can sort of ignore this for the purposes of talking about the Farrell-Jones conjecture. By a deep theorem of Bowers and Grunewald, these outer automorphism groups are arithmetic. And so they satisfy the Farrell-Jones conjecture by another of the results I stated earlier. So this is a look at the short exact sequence and stitch many things together proof. And then to get from outer automorphisms back to honest automorphisms, we use the usual short exact sequence with the honest automorphisms in the middle, the outer automorphisms on the right, the inner automorphisms on the left. You have to do a little bit of work to check that the inner automorphisms were not so different from the group you first thought of. But they're not. And so you can use this suspensions extensions result that lets you combine knowing the Farrell-Jones conjecture for the inner automorphisms and for the outer automorphisms and for some semi-direct products which look enough like semi-direct products of G with Z. And the question that I don't know the answer to, I would like to know the answer to, this is open for the outer automorphisms of a free group whenever n is at least 3. When n is 2, it's fine because it agrees with GL2Z, which is arithmetic. And so since we don't know for outer automorphisms of free group, we don't know for automorphisms or outer automorphisms of infinitely ended hyperbolic groups, even if you say torsion free. This is the thing I would really like to know. We'll stop there. Thank you very much for your attention. Any more questions?
Okay. Thank you very much. I have 2 questions, only one of which I hope will be stupid. So if you have a group and an action of Z via an automorphism, and now you have a ring, then the automorphism of the group induces an automorphism of the group ring, right? And
Yes.
so you can form the cross product of Z with that ring. And I believe that is the same as the group ring of the semi-direct product, right?
I believe so, yes.
Okay. Now, and there is this fundamental theorem for twisted Laurent polynomial rings that computes the K-theory of this cross product in terms of the K-theory of the group ring of the original group and the action. So if this is somehow not useful in your situation to, compute K-theory of cross products, or what's the abstraction there?
The abstraction
You
for
are
me
muted.
No. I don't. Am I still muted?
I still can't hear you.
How about now?
You appear as unmuted, but I still can hear you. Gisela, can you hear her?
Yes, I can
Well,
hear her.
now I cannot hear anybody, so it must
So
be me.
the problem is with our computer.
Let me hang up and connect again.
Okay.
Okay. Any more questions in the meantime?
I'm looking at the chat, but there's nothing. Thank you for the talk.
Of course.
You're no. Hi. Can you hear us?
Still no sound. Okay. So
Hi.
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 Hello.
Hello.
I changed my sound. choice to the headphones, but I still can hear only myself.
I don't know. Okay.
I will. Well,
Strange. Okay, I think I'm going to
I will
stop.
type the short answer.
I'm going to stop the recording, and then we'll see what happens.
Yeah.